Okay, so far we've seen that capacitors contain energy. We saw in the last video with the LED that once you opened up or closed the circuit to allow the capacitor discharge through an LED, at the start there was a big bright flash and then it very quickly dropped off. Okay, but it didn't drop off to nothing quickly. It dropped off and kept on eking out current very slowly for quite a long period of time. And so what we've got to try and do is see if we can predict what a graph of the charge versus time will look like. Okay, so if we sort of take our axes here, we want to know if that's our initial Q, or the full total charge, I'll call that Q0, on the capacitor plate, and this is time, what's going to happen over time? What's it going to basically do? Okie dokie. Now we know, basically what we do know is it starts off steep, don't we, because it was a big current, a big flash, and we knew at the end it eked on for ages. So we're going to get something like this. It's pretty clear that's what's going to happen. But what I want to try and show you is that we're going to get exponential decay. So first things first, basically if we shut this switch here, there we go, we know the current's going to flow through this, and the current in the resistor can be given by, in anywhere in the circuit, can be given by the potential difference across the plates, okay, divided by the resistance of the circuit. And of course, once current starts to flow, once charge starts to leave the plates, the potential difference will diminish, and of course the current will go down as well. Resistance is a fixed value. Now, because Q equals CV, we can rearrange this and say, well, V equals Q divided by C. And so we can arrange this differently. We can say, we'll get rid of the V, let's put Q over C in there instead, and say the current now is equal to the capacitor. The current is equal to the charge divided by C times by R, capacitance times resistance. Okay, so that's our first sort of equation. And the second thing we need to know is what we think about is, well, what is the charge flowing? If we think about as the charge goes through this, how much charge goes through in a tiny little eeky bit of time? What is the value of charge that will flow in a small amount of time dt? So as long as the time is small enough, we can say the current will be constant for that small period of time. So we could say that the small amount of charge, delta Q, that would flow in a small amount of time, delta t, would be equal to I times delta t. Now, the current is going down, okay, so we have to put a negative sign there because it's a diminishing current. But if we could say, well, delta Q is minus I times delta t, and I itself is Q over RC, then what we can do is we can basically get rid of this current term here. We can put that lot in for minus I. I can say now that, well, delta Q equals minus Q over CR, plonking that lot in for the I, and of course it still has to be times delta T. So where's this all going to? Well, basically now if we divide V by Q, what we got over here is we have a ratio of the amount of charge that's left, the amount of charge that's left the plates, divided by the amount of charge that's on the plates, is equal to minus delta T over CR. And what this basically says, what this pretty much tells us, is that it doesn't matter how much charge is on the plates, the ratio of the charge that leaves the plates to the amount of charge that's on the plates is going to be the same for any given amount of time. Okay, so if we said it's therefore the time it took for the, let's say dq, delta Q here was, I don't know, half of the charge that's on the plate. And the time it took, and the original charge was whatever it was, but the time it took to fall from the amount of original charge, Q0, to half, I'll draw this on here now, let's say that was this delta T here, then the amount of charge time it's going to take to go from this charge to half of that will be the same. And so we'll end up with this basically exponential curve. What it's telling us is